So let's begin with a small introduction to Kafka. So when you try to find out what is Kafka on Confluence website or on a main website, there's this blurb in there that says Kafka is used for building real-time data pipelines and streaming apps. It is horizontally scalable, fault-tolerant, wicked fast, and runs in production in thousands of companies. So apart from a dozen buzzwords that will get you a great buzzword bingo, what is really Kafka? It's a distributed streaming platform. It started as a simple log. That's how they call it before. Just a log. You just put data in there, it looks like a log. Now it's a streaming platform with three main capabilities. It lets us publish and subscribe a stream of records. It allows us to store records in a fault-tolerant way, and it gives us the ability to process records as they occur. It has a simple model, a producer and consumer. So it's a publish and subscribe model. They call the publisher a producer and the subscriber a consumer. That means it comes in two bits of software. One is the producer, that's the client, and then the consumer. And the main Kafka application is what you see there is the Kafka cluster. All these records, the stream of records, is categorized into topics. A topic, in order to be fault tolerant, has many partitions. So when you create a topic, you'll create with many partitions. This is how you distribute the partitions, because partitions can be on different servers. And also this is how you can scale your consumers, because many consumers can read from many partitions. And the partitions are also replicated. This is something that happens in the background. You don't really need to think about it, but they're basically replicated to more servers. And important to note, each record is assigned an offset, which is unique and identifies a record within a partition. So as you can see in there, you have partition 0 and with their offsets. And it starts from 0 and it just increments all the time. And this is kind of how they guarantee the ordering of the records for each partition. And the producer is the source of the records. This is, in your application, something that just emits events or messages or whatever you want to do. You produce, you publish data to the topics of your choice. Then the producer has the responsibility of choosing which record to assign to which partition. And this is done by default in a round-robin fashion. So the Kafka client is just going to do a round-robin distribution, and you don't need to think about it. Or if you want to ensure order according to your own business logic, you do it with using a semantic function. Is either a string that they're going to apply a hash on it, or a function that you define yourself. A consumer is a bit more complex. That's because you need. This is where you're doing the heavy operation of consuming those messages, of processing those records or events or whatever you have. The consumer subscribes to a topic or an array of topics, so it's not just one. You have to give them a group name. It's not compulsory, but you have to give them a group name if you want to handle restarts and keep track of the position of your consumer. So partitions are divided by all consumers' instances of a group. Each partition is consumed by one consumer. So when you have let's say multiple consumers, Kafka is balancing the load for each partition to assign an equal number as possible, an equal number of partitions to each consumer. So whenever you are the consumer, it's a rebalancing operation happens, so you'll get less load. This is how the horizontal scalability happens on the consumer side. And very important to note is that each consumer instance with the consumer group name commits back to Kafka the offset. So whenever it reads, as you can see in here, whenever it reads offset 9 from partition 0, it sends that to Kafka and says, I process that. And then if immediately after that it dies, and it needs to be restarted, and it may be restarted after 10 minutes. It comes back online, and it asks Kafka, where was I? And Kafka tells, you're at number 10. So you read offset number 10. Yeah, that's about it for it. You can find more resources and a very nice introduction. You'll see a bunch of the words that I used in there. And there's a nice quick start where you can, in 5 minutes, you can install Kafka, install a user consumer in the console, use a producer in the console. You can send messages, and you can view the messages as they're being sent on your own machine. It's very fast. It's very interesting. Questions so far? Yep.
You can control how long it keeps the existing messages, or it only keeps the person subscriber?
So you're talking about the topic, the Kafka. So Kafka keeps them permanently. There's a TTL that you can apply to a topic. So they would expire the records after a certain amount of days. But normally it keeps them indefinitely. So Kafka in here where it says Kafka cluster. So these are the Kafka brokers, where data is going to be stored. So it receives the data, it stores them in their own internal format, and then if there are consumers for that topic, it sends the data. If not, it just leaves the data as they are. It was called a log because of the this thing, because it's basically you append something to a log. Every time you produce, you just append something to a log, and that's the file. And with their internal representation, it's just kept on disk, and that's it. The data is there. Is persisted. Yep.
Once a producer calls asynchronous, is there a preferred or can you choose?
They default to asynchronous now.
When a producer makes a call to say, please, here's this record, please add it to the queue, is that called synchronous and asynchronous?
It's asynchronous, but you can give it a callback, if I remember correctly. I remember my memory is fuzzy because we moved from 08 to 09, and now we're moving to 010. And at 08, there was an option with synchronous and asynchronous, and yeah, they would give you an acknowledgement. Now it's not like that. It's asynchronous. It has an internal buffer. This is all for performance. You can give it a callback to make sure that you actually processed, and if you didn't process, you retry, or you tell it to retry. So, yep. So here. Yeah.
I see that this Kafka also is published in some support program. So it comes to this commonly called rather than queue. What's the main difference between this rather than in which condition refer to this rather than which condition?
So I'm not very familiar with RabbitMQ. I used it a little bit. I know that RabbitMQ has more strategies than PubSub. And you have different ways of saying, I acknowledge the message, or you retry the message. It gives it leaves the onus on the broker to retry something, and there is a push mechanism in RabbitMQ, and in Kafka it's basically a poll mechanism. So Kafka is a basic publish or subscribe, but internally it's just like you send, and the consumer polls for the data. So. So I'm not very familiar with RabbitMQ that I can really compare it, but from what I heard, there's a lot more options to RabbitMQ. Also, as far as I remember, RabbitMQ doesn't have persistency. Kafka has persistency. So one of the big features that they advertise, but that comes with storage as a cost, is that you can keep all the messages in the queue. And their idea was like, you put all the events in there, and if you need to reprocess them. So you put all the events for, I don't know, let's say put the log, put all your logs in there, all the log lines, you put them in there. And you can stream them to something that's gonna index them. And if the indexer gets broken, you just go and you reread the whole topic again, and you keep all the history in memory. I'm not sure if that's the case, but as far as I remember, RabbitMQ doesn't have that feature.
I see that most active is a message broker. So it's sitting to application. When you
Yeah, if you just want them without the persistence, they're the same. I don't know the comparison in terms of speed, but for me, the main thing that is there is that the persistence gives you also a nice way of having different services to consume data from a topic, and different services can act on their own pace. So one service could be down for a day, and then they could resume processing, and other services could be up to date. So this can happen at the same time. Sorry, there was a question at the back there. Yeah, they're implementing that. So they have at the moment at least once guarantees through the offset mechanism. They're implementing now exactly once guarantees. So at the back there, yeah. So it used to be Zookeeper, and now it's an internal topic, which you can read if you do some things in there. You can read and you can see basically a bunch of records with the topic name, the consumer group name, the offset, and the date. So all that stuff gets put into a topic, and the broker reads that. And whenever a subscriber comes in, restarts or resumes operations, it just queries Kafka, and internally Kafka just reads that topic or has a snapshot or something like that. Yeah, so this is internally. Internally, the increment is done by the broker. So the producer doesn't know what is the offset that's producing. It doesn't need to know, because there could be many producers producing in the same topic. The broker arranges that. When it depends, it assigns an incremental index, and that's the offset, and it's immutable. And then when and the subscriber reads, it keeps track. It gets, when it gets the record, it gets some metadata to it. The offset, the topic, the offset, and I think they will add now an inserted at time in 010. So it's available in 010. So you know exactly when that message was sent and acknowledged by the broker. So that's nice if you want to see, you want to test lagging in your internal application. But yeah, that's basically, it's in there in the broker. And then the subscriber just says, this is where I'm at, this is the offset that I'm at for that partition and topic. And next time when I need more data, I know where I can resume from. Yeah.
Messages, is there any structure to them, or is it just text or binary data?
Whatever you want to put in there. At the end, it goes as binary, but yeah, you have the consumer has like a way of, and the producer at the same time, has a way of basically some abstract classes that tells you to define a serializer and a deserializer. So you basically, you get whatever you want, you get a byte array, and then you transform it in your own object, be it JSON, Avro, whatever you want to do in there. Yep. Okay.
What's your experience of the operational reliability of Katka?
Overall good. After 09, it's much better. Mostly because of Zookeeper. They don't rely as much on Zookeeper. And like, it's pretty stable. We had some issues, but they were mostly down to our, let's say, cheapness. So like we said, oh, we're going to use just 3 brokers. Like you have to install 5 brokers. It works in a similar way as Cassandra with replication and the number of replicas that you have, and to ensure that it's high availability. So in some parts we said, oh, it's 3 is enough, and if one went down, we had some issues. I think overall it's been very stable. It's a simple piece of application. It just sends something and appends it to a log. So it's not complex. Okay, last question. Sorry, can you speak up? I can't hear. Yeah, so that's internally what it does. It just like they have a protocol that they communicate with each other, and then internally the consumer is polling. So it just says, okay, I'm just offset. Give me more that you have. It just doesn't give anything and doesn't receive anything. Sorry. Yeah, it will block for a while and then it will retry. I'm not very familiar with the exact internals. Sergio dealt with some issues like that, so you can ask Sergio after this. Sergio dealt with a lot of niggly issues like this, where it's like, oh, what if it blocks here, but there's another partition that doesn't block, so yeah. Okay, so the next part, which is one of the main presentations that we prepared, was about Maxwell's daemon. And this is an application of what we use Kafka. And this is how we in Zendesk introduced Kafka. We wanted to get the data from MySQL because we have a lot of applications and some old applications that are very, very hard to update. We wanted to get the data from MySQL, which is the business data, the important data, customer data. We wanted to get it into Kafka. And we ended up writing our own piece of software that does that. This is me, you know. So I'm going to talk about what is Maxwell daemon, the data format, and you can use it with stream processing and some example use cases. So in simple terms, Maxwell reads MySQL bin logs and writes raw updates to Kafka as JSON. So with this, you can extract all the MySQL data that any application updates. So you don't need to go to each application to update when something is created. When a new user gets added, you send an event. No, that's all handled by Maxwell by just reading the MySQL data. And it produces a consistent and easy to ingest stream of updates. And with this, it basically adds the ability to add streaming processing to your dataset without changing anything in your code base. This is a sample of insert SQL statement. So all the updates basically get into, because it just replicates the bin log, all the updates end up in Kafka. So in this case, we have an insert into the database test table E, and you set the value M to 4.2, C2 now, comment, and a text. So this is the insert statement, and this is the data that is sent to Kafka. So you have the database name, the table name, the type of the statement. Now it's an insert, the timestamp when it was done, the transaction ID, and the commit. This is basically a flag if it's the last commit in a transaction or the last statement in a transaction or not. And then the position in the bin log, the server ID, the thread ID, and then the data. So you get the SQL data in there, so you can process that. It does a similar thing with an update, except that it adds an old column. So it basically tells you what data was before you updated it. So that's important for you if you want to, I don't know, clear a cache or do something like that. And it handles the same in the same way it deletes. It just sends the old data when it was deleted, so you know what was deleted. And so with the two pieces of information here, the commit and the transaction ID, you basically can combine transactions. And a transaction from an application standpoint is basically a piece of information, because as you denormalize the data, you will end up with a little bit of information here, like I'm changing the user's email, and that's not necessarily in the users table, but I'm also changing the updated at in the users table. So you may want some holistic information view of what changing of a user's email or a password or something like that is. So by using the commit and the XID keys, which is transaction ID, you can use the stream processor to accumulate the data and basically group them by a transaction ID until you see a commit true flag. So this way you can get the whole SQL transactions. Other feature that Maxwell offers is a table bootstrap. So if you already have data set and you want to introduce Maxwell, it gives you a way to get all the data that's already in the database into Kafka. And it has flexible partition strategies. Like I was saying, in a partition, you are guaranteed that you have order. So if you leave it by default, it does a round robin, but you don't know, you don't guarantee the order for anything. So if you want to guarantee order by database table, a primary key of the table, which could be the user ID, account ID, or whatever, you can get that. And it supports AWS Kinesis, which is basically Kafka software as a service. So sample use cases are cache building and expiring, so you can build the caches when updates happen, and when an update to a record happens as well, you can just expire the cache and recreate it again. You can extrapolate business events with this. You can do search indexing. That's one new project that we're working on as well. Instead of going and getting the data from MySQL to index it in Elasticsearch, we're now going to use Maxwell to get the data streamed to the indexer. So everything is going to be done, automatically, and we keep up to date instead of just polling. We get all the data, and metrics collection. So a transaction is, you can see that as a business event. So you can, from a SQL transaction, you can extrapolate a business event. In our case, we work a lot of tickets. So what we've done is we've seen how a transaction, how a ticket-created transaction looks like. And we managed to basically coalesce all the statements in transactions and then pattern match all the transactions into the ones that we know that they are to create a ticket. And we extract data from that, and we create the normal, proper events, business events like ticket created, ticket updated, ticket solved, ticket deleted, and all things. You can extrapolate higher order events than just like simple, the end result is not going to look like that. We're not going to display this to a user. Oh yeah, ticket deleted and the whole data was this. No, we're just going to extrapolate that. We can, by going to other sources, using Kafka as well for caches, we can extrapolate. Oh, this ticket was created by this user, but I only have a user ID in here. But I can go to a cache and get the actual user data that I can submit as well with that.
How do you guarantee the sorting inside the transaction?
So in a bin log, the data comes sorted, ordered. So that's guaranteed ordered. And then we partition by the database. So all the transactions are guaranteed to be ordered in order, yeah. Yep. I'm not familiar with that, so it's not this team that worked on that. It's another team from San Francisco that did. I think in principle it works as just a MySQL replica that reads the bin log. You can look at the code if you're really interested. The code is open source. And here, Zendesk/Maxwell. You can look at the code and see how they did it in there. Sorry, 1, 2, 3. Okay.
Is it implemented as a standard producer, or it uses the Katka connect?
It uses the simple producer, as far as I know.
It's not a Katka.
Oh yeah, no, it's not. I think they have some Kafka Connect stuff for Postgres, and they have a different one for MySQL or something like that. Yeah, and I think they're planning to do similar things for. We've been using this for 3 or more years in production. Yeah. So we trust it with our life now. So, yeah, second one.
I see that you provide a SQL session and more like this JSON. Does it you go to the client, but the persistent are likely to database.
Sorry, I didn't hear that. Can you say that again?
As you provide a single statement,
Yeah.
like update, delete,
Yeah.
and then there's a JSON solved. So the client send a JSON to Kafka, and there's another application subscribe to Kafka and persistent.
So,
Probably I have missed something.
so this Maxwell is not writing data to MySQL. It just reads what MySQL saves, what MySQL commits. So the MySQL bin log is basically the log of all the statements that MySQL accepted and it actually implemented, applied in the data set. So that means that the data is there. So it uses to read that data instead of having like, I don't know, like a procedure for every or everything. It's going to do something. So we just read all the statements like this. So when Maxwell sees this statement in the bin log, it just outputs this JSON in Kafka. And then the consumers will read the JSON statement. Yeah. Sorry, there was, yeah. How many topics in Maxwell? So we have only one topic. Yeah, so that's the topic has many partitions. So the way that we did it was we shard by the database name because we use sharding. So we shard our data across many databases. We end up with, some databases will be on partition 0, some databases will be partition 1, and some databases will be in partition 2. Yep.
Rationale for doing this whole thing at all rather than just having the application write to Katka, so that you said you were extrapolating these higher order besides the crystal and like the great
one reason was the guarantees around if you send an event and you send a transaction, you don't, because you're using two different systems, you don't have a guarantee that one would work and the other one would work at the same time. And if the transaction fails, the event will not be emitted. There's no clear guarantee of that. And then the other thing was our application is huge. It has hundreds of thousands of lines of code. There's other applications that are using the same database, which is not an ideal scenario. That's the way it is. And it was a very simple way, even though it sounds crazy, it was a simpler way to just read the bin log and output all the data changes instead of just going into each place that it might create, update, change something. Because, perusing to hundreds of thousands of lines of code, trying to change something, it's not fun.
They feel responsible or feel ownership that if they change them, they have to tell someone else, so they're going to break this pattern matching.
Oh, so this is something that we kind of now, like the things that we're doing at the moment, they're like the core things that nobody touches, nobody dares to touch. We didn't have any discussion around, if you change the table, you need to know that you're changing that. So I think a larger discussion needs to happen in regards to if you extract the data from Maxwell and you own the tables, just when you migrate, be considerate of the patterns. But at the moment we have very limited subset of limited subset as in there's hundreds of tables and like 4 or 5 of them are pattern matched. Yeah. Yeah, it can be installed as a replica, so not necessarily on the same machine as. I'm not familiar with that level of detail, but yeah, you can install I think we have an installation of just MySQL. We don't use Aurora or anything like that. So we just install it as what's the name? As a replica. So we have our own MySQL installation, and we just install it as a replica, and it just reads the bin log as any other replica would. So it receives as a replica server, it receives all the data that the master will get. Yeah, I don't know if there's an integration to AWS or Aurora or whatever. Yeah, but so this is only for MySQL. That's the thing. Yeah. Yeah, so Sergio, to the next talk, of time now because it takes a little so Sergio's next talk is going to be on how we use Maxwell to build a service, mobile push notifications. So we can leave Sergio, we can take a break for 5 minutes. There was one other question here.
Effectively, you have a second database in a completely different file format. Is the file format is the structure? I presume that this space is not a problem for you.
It is a problem. So, yeah, the data space is cheap. You know, hiring engineers to code is more expensive. So. It's part of the trade-offs, and we have the topic is expiring after a couple of days because we don't persist all the data all the time. Okay, thank you very much for this. If there's other questions, we can come to me and speak directly.
Okay, let's start then. So my name is Sergio. I work as an infrastructure engineer here in Zendesk as well. And today I'm going to speak about a possible use case to apply the stuff that Andrei just talked about. So he pretty much laid the foundation for this presentation. So we had to build a push notification system. We had to deliver real-time notifications to our mobile users. And so the way we started approaching this was by seeing what we had available in the company. One of those things was Maxwell that Andrei just explained how we could use it. The other thing was Kafka. So we already have Kafka in the company, and we started exploring the framework. Okay. So this is me, as I just mentioned. So if you ever need to reach me out for some questions around Maxwell or any of the stuff that I'm going to talk about, you can use my Twitter handle, for example. And this is the agenda that I'm going to talk about. So you're going to see how we deliver real-time notifications using the systems that we just saw Andrei talking about. And we are going to also discuss how can we monitor a system that has been built in top of these services. And then we are going to see some of the challenges that we had along the way approaching Kafka and dealing with a distributed system like this. So with no more delays, how did we use Kafka for real-time notifications? So this was some of the initial requirements that we had from products. So we had to be able to react to any database event that could be translated into a notification. So this touches what Andrei just mentioned about getting all that database information and translating that into high-order events. So for this to be able, we had not only to process all this data coming from the database, but we had also to aggregate that into transactions to build some context. So we were not interested in getting all the database updates, inserts, etc. We wanted to be able to correlate all those separate events into the same transaction. So we had to understand which events belong to the same transaction so that we could get the full context of that action that the user just did in our main product. So once we have these transactions rolled up, as we call it, then we could translate those transactions into the order events that I just mentioned, and finally translate those events into real notifications with all the information that we needed to be part of the body of those notifications before we push them to the mobile devices. Also, we had to tackle and address all this, but at the same time, we had to guarantee that the push notifications were being delivered in real time, because we don't want to put a huge delay on this process. We also wanted to deliver these notifications in a sane order for the user. So imagine if we create and update a resource, we don't want the update to reach the user before the actual creation of that resource. So that was a big important requirement for us as well. And finally, something that the mobile team asked us to try to achieve was an accurate batch count. So a batch count per user is given by the number of unread notifications that user has. So that's, for example, that little red marker in the mobile app when you get a push notification in the mobile phone, so this in iOS. And so this red marker that gets incremented each time you get a push notification, that's what we call batch count. So we had to make sure that this batch count was always accurate in each notification that we pushed to the device, as it's part of the body of the notification. And this is the architecture of the system that we came up with. So we can see already here as how Maxwell fits in this architecture. So it's streaming or reading all the events that go into the bin log, as Andre mentioned, and then it's putting all those events into Kafka. Then we are processing those events into what we call a transactions processor. That's where we aggregate all those events and into transactions, and we finally write the transactions back into Kafka. And that's where we reach the notification service, okay, which I will explain a little bit further on the presentation. So some of the challenges that we had from the very beginning, some of those already addressed by Andre, were that we had to process all those events from the database in the same order that they were happening and read from the bin log. So the way Maxwell approached this was by partitioning this data that it goes into Kafka according to a specific partition key. In Zendesk, because of the way we shard our databases, all data regarding an account always goes to the same shard. So by partitioning by the shard name or the database name, we had the guarantee that all that data that we were consuming was already ordered by account. Okay, so that was an important requirement, let's say, or important guarantee that not only Maxwell but also Kafka gave us by the way we approached the partitioning of this data. Finally, or not finally, sorry, but then we think about the transaction processor, when we are aggregating all those events and getting the full transaction, before writing to Kafka, we also had to make a decision regarding how would we order or guarantee the ordering of these data that we just want to write back into Kafka. So we had two options here, either writing or partitioning by account or by user. Because this transaction processor is used across many other products in the company or services, we decided to keep the ordering by account. So all the data that gets out of this transactions processor will be ordered by account as well. This is achieved by partitioning this data by account ID. So we no longer deal with database names. Now we are actually partitioning this data by account ID. Okay. And then we get to the notification service. So as I was mentioning before, one of our requirements was to, again, order that all those notifications that we want to push to the mobile device per user. So we wanted to deliver these notifications with the same order per each user. So the way, again, how we approached this was by partitioning all this data, all those notifications by user ID. So we can see here on this notification service, when we read the transactions, we have this event stream that is processing the transactions, translating them into those high-order events that I was talking about. And then those events are going to be written, partitioned by user, back into Kafka. And finally, when we consume those events, they are going to come ordered by user, and we are going to transform them into notifications that we then push to the mobile device. Sorry, on the notification stream, that's where the calculation of the batch count happens. So by always consuming that data ordered by user, we are sure, or we can guarantee, that that data is going to come in order. So for each notification that we are about to push to the mobile device, we just calculate the batch count at that moment. And then when we push the notification, the batch count is going to be accurate. Okay. This also allowed us to eliminate some race conditions that we could end up while calculating the batch count, which become even more important when we were asked to do this. So throughout the project, or in the middle of the development of the project, we were asked to provide an API that would allow users to mark notifications as read. So at the time that when we had to implement this API, this was a big challenge for us, because we were thinking, okay, so this is a completely separate part of our application that is going to tackle or to touch the batch count calculation as well. Or could we achieve this without ending up with race conditions calculating these values? So the way we ended up implementing this was by creating the concept of a batch update notification that we then just write into Kafka as well. Sorry, I wrote notification there, but that's a batch update event. So by writing this into Kafka, also partitioned by user, we guarantee that whenever a user marks a notification as read, this event will be written into Kafka to the same partition where all the notifications regarding that user are going to be. So it will be consumed in order as well by this notification stream. And so the batch update that needs to happen from marking notifications read will follow the same order as any other notification. So it will update the batch count correctly as well. And so this was some of the conclusions that we reached at the end of the project. So the project's been in production for like 6 months now, and working just fine and fulfilling all the requirements that the mobile team asked us to fulfill. And along the way, we had some ups and downs, but this was pretty much our overall conclusion of using both Maxwell and Kafka to support this project. So Kafka is advertised as being like really lightning fast, and we verify that. So it was really good, good experience to see how fast it can be. And even though, as Andre mentioned, in some of our data centers, we started by running just with 3 node clusters. In some of others, we decided to go with 5 node clusters, even though, or either way, it was super fast dealing with all the data that was coming from Maxwell. This data, like even without being under loads, we were reaching numbers like this, like can be consistently streaming at between 7,000 to 10,000 database events per second. But during load, it can like perfectly spike to 25,000 events per second, which is pretty much over 1 million events per minute. So this is even before rolling up this data into transactions. Another thing that was really good that we got from Kafka was the ordering guarantees that it can provide, even though it's fully distributed. Like the way it deals with partitioning and how it allows us to partition the data in order to guarantee the ordering was something that really matched our needs, and we were able to use that to guarantee all that ordering that I was talking about. Another thing that we found out is that Kafka is highly configurable, not only from the cluster point of view, but also the producers and the consumers. So there is a lot of configuration that can be tweaked and tuned in order to be able to reach our needs. The challenge sometimes here is understanding all that configuration because it's so vast that it's really hard to know from the top of your mind all the settings that are available that you can tweak in order to make your system more performant. And the other thing that we saw is how easily it is, how easily scalable, sorry, it is. So Kafka allows you to scale it horizontally. Not only it's fairly easy to add or remove nodes from the cluster, from the Kafka cluster itself. And I put easily under double quotes because, of course, there is always some data replication and data rebalancing that needs to happen when you add a node or you remove a node. But at least the ability to scale it is there. So, and recently we actually had to scale the cluster, and we saw how easy it was. And finally, from an application perspective, it's also very easy to add or remove consumer instances. So if you want to, or if you need to increase the throughput of the system, you can fairly easily, again, add new consumer instances so that you can increase the parallelism of your application and process more data. So this was pretty much the experience that we had over the last year that we've been developing this system and maintaining. Any questions so far?
What was the average size of the message?
That's a really good question. So the events itself, they vary a lot depending on what part of the product is creating those events. So in average, the events are really small, just a few thousand of bytes. But we saw some, especially our help center can create like really big events. That was a big challenge for us. Sorry, because not only those events were already big, but the transaction that we then roll up from those events can become even bigger. And we, as part of the configuration tweaks that I was talking about, we had to actually increase the message size, the maximum message size that we can write and consume from the cluster. So write to the cluster and consume from it. So yeah, the good thing is Kafka deals very well with the load, not only in number of events, but in actual size, like megabytes of data that you can actually stream through Kafka. So that was good. The cluster itself was able to deal with it. The application side, not so much. So we had to tweak it in order to be able to deal with those big messages.
Was it fragmented message? It was like 10 megs.
Not really. So the Kafka deals with chunks of data, and you can assign it. You can say, for example, that I want to be able to process 50 megabytes of data, each chunk of data that it's consuming from the cluster. But for example, if one single message is bigger than those, 50 megabytes, it won't partition that message. So that message has to be consumed. So there's no way out to run from that. Okay.
I presume you had a separate topic for each of the stages in the cascade?
Yep, we had. So that topic that Andre already mentioned, so where Maxwell writes its data, so that's a separate topic. And then for each one of these phases, we have separate topics to which we write the data. And again, this is because each topic has its own purposes and it's partitioned on its own different way. So we had to create different topics for each one of those stages.
The guarantee of the decrease is at least one. I guess on each step you
need to manage duplicates. Yes. In our case, we are not, because it's push notifications, and we thought, okay, if the user gets twice the number of notifications, that's fine. What we want to guarantee that is that at least it gets one notification. So that's the decision that we took. So I think someone asked a question, I don't know if it was you as well, about the delivery guarantees that you can reach with Kafka. So depending on the framework that we are using, that you use to consume from Kafka. So for example, we are using what used to be reactive Kafka, and it's now turned into Kafka Streams. I think that's the name of the library. And they provide more delivery guarantees. So you can use at least once. You can, I think they already had support to exactly once. You also have another one, at most once. So you can play with these frameworks, or you can configure these frameworks to deal with those concerns for you, let's say. But our decision was to, if we deliver the notification twice, it's better than not delivering it at all. So the decision that we took. Yes? Sorry? To reach the peak. So these numbers were taken from one of our biggest clusters, and on that cluster we have 5 nodes processing. But these numbers depend a lot as well, of course, of the load that the actual product is producing. So in that case, I was mentioning that we've seen it spiking to the 20 to 25,000. It could handle perfectly much more than that. That's the maximum that we have seen until now. Yeah.
That was in one topic as well, no?
Sorry?
That was in one topic as
and
well.
That was in one single topic, the one that Maxwell writes to. Yeah.
You use Kafka at 3 different stages in this pipeline. Is it the same Kafka deployment or separate clusters?
It's the same cluster. Yeah.
So just
several
different topics. So you're consuming from Kafka and then writing back a new event.
Exactly. Yes.
It was more or less already answered, but so you have no kind of optimization at any level, like kind of buffering of the notification, then merging all together. Like if I have A to B, B to C, I notify only A to C, or if I have A to B, B to A, I don't notify anything. I mean, I wanted to ask the same for Maxwell, so I don't know if there is something at Maxwell level. So like you have 2 inserts, 2 updates, and you get only the second one, or 2 updates that at the end are not modifying anything because you update to B and then you update back to A. You have no optimization like to avoid notifying something notifying no change.
Not at the moment.
Sorry?
In the case of an undo.
Yes, or undo, or you have an update A to B, B to C, and you notify only A to C, or you have A to B, B to A, you don't notify anything because it's just nothing happened. Like. Or you notify everything.
So at the moment,
you say that you don't even remove the duplicates. So I think you don't.
So at the moment we are dealing with each transaction on its own. So even on a situation like that where you produce a transaction, but other transaction comes that pretty much rolls back what was originated on the first transaction. We are not dealing with that at the moment. You could say that, again, depending on the framework that we are using to consume from Kafka, you could have like buffering mechanisms in order to imagine you consume a transaction, you hold it a little bit, you consume the next one. But this type of thing, so we didn't want to go down this path. First, because there was no such requirement from our product team. Second, because we want to deliver as fast as possible. So this buffering will introduce a little bit of delay. So we are, at the moment at least, we are just dealing with each transaction on its own as a separate event or a separate context. So we are not waiting for the next one in order to see what to do with the previous one.
And sorry, second question. The user you're talking about there is the login of the app in the phone, or is a user identifying uniquely the phone?
Can you repeat again, sorry?
When you talk about user notification there, is the login of the app in the phone, or is the phone itself? So if I have 2 phones with the same login, with the same user, does the mechanism of the API server read?
We'll deliver 2 different notifications. So each device, so imagine, you as a user can have 2 different devices. So those 2 devices will be registered against our system. So when we are about to send the notification, we are going to get all the devices that are registered for that user, and we are going to push to each one of them. Then it's on the user to decide if he wants to receive notification or not on that device.
In the pipeline, I presume you do some aggregation, I think in the last step.
Yeah. So
do you use any intermediate storage?
We use Cassandra. So I didn't explain it's very into a lot of into a deeper level of detail, but we use Cassandra to store not the events itself. So the events are just in Kafka, as Andre explained. So Kafka also guarantees that the events are there stored. Not events. The messages are there stored in the file system. So if we need to process them again, if something crashes, that's just going to be consumed again. What we store is the notification. So whenever we send a notification, we store it in Cassandra so we can keep track of what we have.
Does this introduce any latency? And what is the maximum latency that you have at peak time or when you have spikes? So from when you receive the event from Maxwell until the end?
Mm-hmm. So under normal behavior, the latency is like 1 second, 2 seconds at the most. Mm-hmm. We have a huge dashboard that keeps track of all the latency across each one of our data centers. And under normal behavior, that's the latency that we get. Writing to the database does not introduce that much latency because, as I mentioned, we are using Cassandra. Cassandra is like excellent for writes. There's a huge write throughput. So the latency in there is like small number of milliseconds. During spikes, however, so it's not actually spikes because during heavy loads, the system still reacts pretty well, as I was mentioning. So when we are talking about 20 to 25,000 events coming from the database, the system can perfectly handle all that load, and the latency almost doesn't even change. Where we have seen some latency is when, and this was kind of a surprise that we only noticed later on in the project, if you have jobs, massive jobs running, like deleting data or in MySQL or inserting data or something like that, that produces such an amount of events like in that single moment.
We see the same.
Yeah, so that's super hard to deal with. We are trying to have mechanisms to deal with these spikes, but that can introduce latency. And I'm going to explain later why. But you can imagine that this massive number of events for one single account usually can impact and affect the overall performance of the system. I'm going to explain later
we experience
why.
The same, that at the beginning we produce a number of events, even for simple, let's say simple.
Yeah, that's really hard to manage. Yeah, the question, right?
My question was very similar. And the question is, how do you compose these higher order events? How many are these higher order events? And do you keep them all in memory?
We try to not keep too much data in memory, to be honest, because again, like looking at the load that we are getting, very easily we could reach our heap size, let's say, and crash the application with a lot of memory. So we try to avoid keeping the events in memory. So, and that is kind of given by the framework that or the platform that we are using. So we are using Akka streams for processing all this data, and that's really good because it allows you to do stuff like you consume a message, you process that message in one stage. We have like 5-6 stages on that stream, and you don't get more messages. So you don't read more messages into memory until that one is processed on that stage and is sent to the next one. So you can imagine that our stream was this number of stages as well, and one message is only received from Kafka as soon as the other one moves down the stream, and so on and so on. So you only keep in memory a certain number of in-flight messages, so that never gets out of control in terms of how much memory you are taking from the system. Also, that kind of imposes a concept of back pressure. So if you have some latency talking to the database for some reason, if the database is not performant, or we have some third-party service that we are using that is having some delay into your processing, the whole stream will back pressure, so you don't consume more data until we are actually done with processing the data that is currently in flight. So that also saves us from getting into problems with the memory that we are using in the system. Regarding the number of events, so we have a few different events that we deal with. It's pretty much 5 different events. One example is create ticket. Another example is adding a comment on a ticket. So this is the type of high order events that then we need to send to our users. So the way we process these data is we get the transaction, we extract only the bits and pieces that we are interested in, and we create our own model with that information that we then transform into a notification. And the notification has its own specs from each one of the platforms that we use, either Apple or Google. So we use a middle model or a model to contain that information before we transform it into a notification. So that answers your question?
Yeah.
Okay.
Thank you.
Yeah, one more question because I really need to move forward.
Thank you. So it's a follow-up question for this one. Basically, when you receive stuff from the Kafka, from Maxwell, basically, you get multiple events of writes within the same transaction. So you need to aggregate those. Do you keep stuff in memory in that case until you have the commit message and then you actually purge?
That's a part of the system. That's a good question. That's a part of the, or good catch. That's a part of the system where we keep stuff in memory. So on this transactions processor, when we get an event, so we keep track of, let's say we get an event, we know that this has a transaction ID. So each one of those events, or the last event on that transaction, will have a commit flag, let's say. So when you get a different transaction ID, you need to wait for the commit flag for that transaction, or to an event that comes with a different transaction ID. Because imagine if for some reason you lose the message or the event that contains the commit flag, you still need to move forward, right? So that's a buffering that we have to do on the transactions processor. So we keep accumulating the events that are contained within the same transaction until we get the commit flag or the transaction ID of the next transaction. So at the most we have 1-2 transactions in memory if everything is proceeding as expected, let's say.
Is this not lossy? Aren't you going to lose messages if there happen to be more than one transaction simultaneously at the same time?
More than
so
one
let's
transaction?
say you have 2 transactions happening at the same time, and while some operations of the first one have already executed without a commit, something in the second transaction happens, so you're actually going to lose the first one. But then the first one is still going to close and it's going to be fine.
Yeah, as far as I know from the way MySQL writes the bin log, all that is going to be sequential in the bin log anyway. So it's just going to be a sequential order of events. And this part I'm not fully sure, but I believe that when MySQL flushes the transaction to the bin log, all those events are going to be in order for that transaction anyway.
Cool, thanks.
Yep. Okay. Thanks. Okay, another part that I wanted to talk about is how do we monitor a system like this? So as you can imagine, it's not an easy task because not only we have to answer all these questions. So if we are getting messages from Kafka at all, or how fast we are reading those messages, or how much are we lagging behind if there is some latency in the system. But at the same time, we also need to capture some metrics to answer all these questions, and we want to produce some alerts. So if something in this system that is built from so many loose components is not behaving as expected, we want to be alerted and react as fast as possible. So metrics are easy to report. So application metrics in general, this is part of our code. So if we have a monitoring system of some sort, in our case we are using Datadog, our own code in the application can just be keeping track of how many events are we consuming, how many events are we producing, and we can just report this to the monitoring system. But this still doesn't answer the question if Kafka itself is actually behaving as expected. For that, there is a very important metric that I think even Andre already mentioned, which is the consumer lag. So we saw in the previous talk that when a consumer reads a message from Kafka, it commits back the offset of the message that has already been processed. So that's what we call the consumer offset. In order to understand if the consumer is lagging or not, if it's keeping up with the load that the producer is producing, we need to know not only the size of the partition, but also what was the last offset processed by the consumer. And the consumer lag is given by the difference between the size of the partition, which is given by the last offset produced by the producer, and the consumer offset, which is the last offset processed by the consumer. The reason why it's so hard to get this metric in particular is because this information is not centralized in one single place. So the consumer knows about which offsets it has produced, even though it commits back to the broker. And then the broker knows about which is the partition size, which is the size of each partition that it owns. Now, you could ask, so if the consumer is committing back the offsets, the broker should have all the information that we need in order to get this consumer lag, and it should be able to roll up this information. It's not doing it. So for some reason, the broker, even though it gets all these offsets committed by the consumer, it treats this information as if it's not his responsibility to roll up this consumer lag, let's say. So in order to keep track of something like this, we had to use another service called Burrow. So this was built by LinkedIn. So LinkedIn was the company that actually implemented and developed Kafka. And I guess they also had the need to keep track of the consumer lag. So they created this application that you can deploy as a sidecar service to Kafka. It can even be on a separate host. And this application, so this service, is just making queries to the broker to get the current size of the partitions, at the same time as it has its own consumer that is keeping track of the offsets that have been committed to that special topic that Andre mentioned. So there is this special topic called consumer offsets, to which the consumers write back their own, the offsets that they have processed. So this service is keeping track of that and at the same time of the size of the partitions. Then it rolls up all this information and it exposes a REST API that we can use to gather this information. So having this, we could just build an application that would hit this REST API and get this information, because there is a lot of information provided by this API. But we actually found out that there is already a plugin available that you can install in the Datadog agent that is running can be running on the Kafka machines. And what this plugin is doing is hitting that REST API for us, getting all that data, calculating the consumer lag, and then publishing it back into Datadog. So that was perfect for us because we were already using Datadog as a monitoring service. So with this, we had all the information that we needed to keep track of the consumer lag, and we were able to build graphs like this. Is that a question?
Two questions. So this is working in terms of bytes, the offsets, not number of messages.
So the offsets are actually numbers. So that's the position of the message in the partition, let's say, so on the file system.
But if you submit a message that's 1 megabyte, is that offset increment by 1 or another?
By 1. So the offset is completely separate from the message. You have your message, let's say a producer produces a record, writes it into Kafka. When the broker gets this record, it will assign it an offset. Then it will store it in the file system with that offset. Okay, so the offset is just a pointer to that record in the partition, and that is a sequential pointer, let's say. Okay.
The other question is, so is Borrow just a regular consumer?
So it's much more. So it has a consumer that is just fetching messages from that topic.
Between lag in your consumers and lag if Burrow starts lagging?
That's a very good question, because we had that issue because the consumer in Burrow can actually go down as well, or just stop consuming. And what usually happens in that case is you see this graph just going up, 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 and our first reaction when that happened was to restart our system, because we thought that it was our consumers that were lagging, when it was actually Borrow that was not behaving as expected. So we had to restart the Borrow. Yeah, it's not very common. It's very rare.
What's scary is using Kafka to keep the data that you're using to monitor Kafka. It's not working right.
That's why I was saying that it was a surprise when we found out that the broker was not keeping track of the actual consumer lag. There are other techniques, a little bit more hard. You can use JMX and connect to your actual consumer, let's say, and then connect to your broker, so you can gather these metrics as well. Because in that case, you are completely dodging the dependency on Kafka, right? You are just connecting to your application in runtime, getting the consumer offsets, and then you get it from the broker as well, through JMX as well, and you can calculate those things yourself. But it was just too much effort for what we had to come up with. And this is just monitoring, let's yeah, so this was how we achieve the monitoring part, and how we managed to know if something is not behaving as expected throughout the entire architecture. Now, to finalize this presentation, I would like to share some of the challenges that we had along the way as well, while using Kafka mostly. So the first one, probably the first one, is actually interesting because, and it was driven by the fact that we didn't understand quite well the Kafka horizontal scaling. So in the documentation, they very often say that the partition is considered the unit of parallelism in Kafka. So when we created our topics, we just thought, okay, let's go with 200 partitions. And that was because the Maxwell topic had already been created with 200 partitions. And they did it that way because they wanted to have like as many partitions as we have shards across our data center. So we just copied the same configuration. So we created our topics with 200 partitions as well. The more the merrier. But at the same time, let's think, how many consumer instances did we actually had in our application? So Andre mentioned this part. When we create partitions, or when we come up with a number of partitions, the idea is to have the ability to scale horizontally our consumers as well. So at the maximum, we can have as many consumers as we have partitions. We cannot have more than that, because if we have more, they won't get partitions assigned, so they will never process any data. So at the most, we can have as many as we have partitions. However, to have 200 consumers, we really had to have like really powerful machines. But when we launched the system, like when we came up with some capacity analysis, let's say, to understand how many nodes we needed, we thought, well, we'll only need 2 nodes, probably 4 cores in each machine, which at the maximum, we thought, well, this could support easily 4 instances, 4 consumer instances in each machine, which in the total gives us 8 consumer instances for 200 partitions. So now you guys ask, did we really need 200 partitions? No, we didn't. So we went completely overboard with the number of partitions. What was the problem is that not only sorry, getting a little bit of water. So the more partitions that we have, the more consequences you can end up with in your application. So there is a very nice blog article in the Confluent blog explaining how to choose the number of topics and, the number of topic partitions in a Kafka cluster. And you see how many consequences there are. So not only from memory perspective, because in the application, the consumer needs to allocate as many buffers as there are partitions, so that has a direct impact in the memory in the system. But there are also other consequences, especially when the cluster needs to rebalance data. If some node goes down, for example, if we add or remove nodes to the cluster, if we have a lot of partitions that can increase the unavailability of the broker, of the cluster. So there are some consequences that we didn't think about because we didn't know at the time, and we actually decided, okay, so let's reduce the number of partitions into a sane number, what we thought it was a sane number. The problem with this is that we can easily add partitions to a topic, but we cannot remove partitions from a topic without recreating the topic. Now, doing this with a live application that was already in production, that was a bit of a challenge. And this is how we felt. So the process to delete or to reduce the number of partitions is pretty much highlighted in here. And you can imagine the effort. So we had to create a second version of that topic, make the consumer read from both of them, because the consumer can read from multiple topics. Then we had to make the producer write to only the second version of the topic in order to be able to wait for the first version of the topic to be drained by the consumer. And only then, when we were sure that there was no data in that topic, we were able to recreate that topic with the correct number of partitions and finally make the producer write only to that first version and have the second version of the topic drained. And like finish this with having the consumer reading only from the first version. So a bit confusing, but a lot of effort going on in here just to reduce the number of partitions in the topic. So if you ever need to think about these things, the recommendation from Kafka documentation itself is to start with a low number of partitions, the number that matches your needs in terms of parallelism and throughput. And of course, you need to do some capacity analysis for that. And then if you need to scale your application, then you can start increasing the number of partitions in the topic as you increase the number of consumers as well. Other challenge was unbalanced partitions. So this touches very close what you were asking earlier. So having the data partitioned by account gave us some advantages. So the account's data gets load balanced across the cluster and gives us the guarantee of ordering that data per account. But it also has a major disadvantage. So as you can imagine, if we are partitioning the data across the different partitions per account, it means that some of those partitions can become heavily unbalanced if we have like accounts that are much bigger than others, and of course we have. So this introduced a big challenge that, and to be honest, there's not too much we can do around this, which is whenever that big account is producing a lot of load, either because of suffering with a lot of load or because there is some job that is running on that account that is deleting data or creating batches of data, this can produce a lot of data into that single partition, which will just make the consumer that is assigned to that partition slow down. And there's no way we can get around this without having mechanisms to mitigate that data that is going to that partition. Or if this is something that we never tried, but I saw references to it, if we can actually manage to have as many consumers as we have partitions in this situation. So if we have as many consumers as we have partitions, at least one consumer is dedicated to that partition, and like we are consuming as fast as the consumer can deal with that load. That was the only way that I saw that we could address this problem, but we are not there yet. So we are actually trying to find which mechanisms are actually producing all this load so we can mitigate those.
Can you bind a single account to a partition?
A single account, that's what usually happens. So when you partition the data per account ID, all the data regarding that account goes to that single partition.
It's run robin, five partitions, say run robins each. Or can I designate one partition just to the big account?
Oh, sorry. So you mean that only that account will end up on that partition?
This customer is this one partition, all the rest of them are run robin.
Yeah. I think, yeah, you can definitely do that in the producer. So the producer, as Andre mentioned, is the one that is responsible for choosing the partition that you are going to write the data to. So you could actually come up with a partitioning strategy that would assign all the data for an account to one single partition. But that probably would not solve the problem that partition is still going to be much loaded, let's say, than any other partition. So in the other side, so in the consumer side, you still need, because that's where you actually need to deal with that load, right? So you need to make sure that we have enough resources to drain that partition. While if you have a low number of consumers that are dealing with all those different partitions, it can happen that at some point the consumer is dealing with a partition that is not actually heavy loaded, and the partition that has a lot of load is just waiting for a consumer to start polling from that partition. So the action has to happen or needs to happen on the consumer side in order to actually address this problem, as far as I believe. That's what I was saying. We haven't, so we are still mitigating and dealing with this. So we are trying to find which services or which things are actually creating all that load and try to mitigate those and try to see if that load should actually be going into Kafka, for example. So we are trying to address this first, and only if we get to the point that, okay, there's nothing we can do from the other services point of view, if we cannot stop this data to flow into Kafka, then we probably need to start thinking on scaling all these hosts or machines that are where the consumers are, so that we can actually deal with this load. Yep.
Yeah, just got proposed. Won't fix latency for that one client, but it will isolate that client from causing latency to the other clients.
Yeah.
So if you look at these 2 points, one is can we isolate, and that will help. The other one is how do we actually fix it for that big client, which is the one that is paying most. So
yeah, that's actually a good point. So what Francisco is saying is that making sure that all the data regarding that account that is heavy loaded goes only to that single partition isolates the problem from any other account. So we can actually keep consuming all the other accounts, and we won't affect the other accounts because of this specific one that is producing all this load. So that's a strategy that we could consider, yes. Yeah, so I already tackled all these points. Okay, so other challenges that we had was, and I just talked about them, was increasing the number of consumers. So in some occasions, as I mentioned, we had the need to increase the throughput. The recommended solution in Kafka is to add more consumer instances, so we can increase the throughput consuming from Kafka. The problem is that we only had 2 hosts, which means adding more consumer instances had to be done at the application level. So as I mentioned before as well, we are using Akka streams, which does not help tackling this way or addressing this through this strategy. That's because, in Akka streams, we have a lot of threads that are just being spawned in order to deal with all this load. So increasing the number of consumers will actually mean that we are replicating our entire stream in order to deal with, in order to be able to support different consumers. So replicating all these streams means that our number of threads is just going to spike by some multiplier, okay? And this started causing us issues at the JVM level, because we just didn't have enough resources in terms of CPU power to deal with all these threads being spawned. So at some point, we actually had to add more nodes to the system. So we decided to scale horizontally. We went from 2 nodes to 4 nodes at the time. And we also scaled up those machines. So we had 4 cores, as I mentioned before. We increased to 8 cores so that we could at least increase the number of consumers on those specific machines. So you can imagine, so it's 4 nodes times 8 consumers, at least in each one of those nodes. We try to keep 1 consumer per each core, which would allow us to scale to 32 consumers. What we found out is as soon as we added more nodes and we scaled up those machines, we actually didn't need to add more consumers, because we could just use the Akka streams configuration in order to increase the size of the thread pools on those machines. That was more than enough to deal with the load. So in the end, we kept the number of consumers low, and we just played with the configuration in Akka streams. not a challenge. So Andre also mentioned this. Sorry, Andre, I keep calling your name. So when we started these projects or these services using Kafka, we started with Kafka 0.8. After a few months, so Kafka released 0.9. So Kafka has been really active, or whoever is taking care of Kafka is Confluent, is really active releasing new versions of Kafka. And in each new version, they introduce a lot of improvements on regarding the previous version. A surprise that we got when we upgraded to 0.9 was that suddenly our application just at some points just stopped consuming. And we were not understanding what was going on. And when that happened, the consumers or the broker would just start rebalancing the consumers, and it was a big surprise for us. So one of the problems that we found out was that, as I mentioned before, we increased the size of data that we could actually consume from Kafka to deal with the big message size. And that introduced a problem with Kafka 0.9. So processing those big messages introduced some delays in the stream. Not delays, but introduced some processing delays in dealing with those messages. And because the consumer at this time in 0.9 is single-threaded, the polling mechanism was not happening. So imagine the consumer received the message, and until that message got processed, it wouldn't poll for the next message. And then, by surprise as well, we found out that heartbeat mechanism in this consumer in 0.9 is actually tied to the polling mechanism. So whenever it polls for the next message, it also sends an heartbeat to the broker in order to say, okay, I'm still alive. So because we were taking a lot of time to process those messages, like postponing the polling, the broker was thinking that the consumer was dead, and it would just start rebalancing, and so on, and so on, and so on. This was like really bothering. It was really bothering for us because we had to revert the whole upgrade for a few months. And so at the time, some of the solutions that we saw in the internet or in the technical forums, we haven't applied them. So this is just what most of the people were saying that fixed their problem, was to reduce the maximum size of data consumed, which we couldn't because we had to deal with those big message sizes. Another possible solution was to increase the consumer session timeouts and prevent it from expiring before processing the data. So this is what was making the broker think that the consumer was dead. So there is a consumer timeout that if the heartbeat takes longer than this timeout to signal to the broker that the consumer is still alive, the broker will just think that it's dead. So a way to fix this is to increase this property. However, that was yet another surprise. We found out that in the broker, there is a setting that limits the maximum value that you can assign to this property, which is a property from the consumer. So we tried to increase this, and then we started getting exceptions because the broker would not accept this setting. It was funny because then we learned that in Kafka 0.10, which brought even more improvements, the consumer session timeout, the setting in the broker is actually much bigger than the consumer session timeout that we have in the consumer. So we were just okay. So anyway, so we had to park the upgrade, and we gave it another try recently, which went better because part of the load that we were doing at the time was dealing with the Maxwell, which was extracted to the other service that I mentioned before, the transaction processor. So that took out a lot of load from the notification service and allowed us to finally upgrade to 0.9. And that's the end of this talk. Is there any more questions?
To these slides where you explain. Can you please go back to the slides where you explain how to reduce partitions?
Sorry?
Yeah. When you create topic version 2, how many partitions did you set?
So this one was set with the same number. Do you remember this better than me, Andre? Probably. But I think it was set with the same number of partitions that we wanted to assign to the new version of the topic, right?
Okay. So when you drain the topic v1, why you needed to create it again? Why didn't you use topic v2?
Can you repeat? Sorry.
When you drain topic v1.
Yeah.
Why did you need to create a new one with the number partition that you wanted instead of using topic v2?
Well, just because of naming, to be honest. So we could stick
just to
with
keep the same name.
Yeah,
Okay.
we could stick with the
It was a bit strange, you know.
As far as I remember, that was the reason why. It was just to keep the.
Yeah, we didn't want V2 at the end of a topic name and then wonder what happened with V1 and if V1 is a schema name. So.
Exactly. Any more questions? No.
Any questions on Maxwell or the Kafka questions? You can ask them now.
Someone was asking earlier about blocking in the consumer, right? I don't remember who was that. So I had to remember because it's been a long time since I checked that. But I was checking on the documentation. So when the consumer is polling for messages, it has a timeout, so it always blocks until waiting for new messages to arrive at the topic. So only when it reaches that timeout, it's considered that there is no more data. And as far as I remember, it shifts to the next partition or something like that. I don't remember quite well. But it blocks waiting for messages to arrive at the topic for that timeout. That's it.
Sorry, just in your architecture, the device at the end, is that a consumer as well? The mobile device?
No, sorry. No. So I didn't represent this in here, but we know that this moved. So the notification stream is the last consumer that we have. So it's just consuming the events that we transform to notifications, and then we use like a separate service and an external service to deliver notifications to mobile. So all we do is an HTTP call, an API call to that service in order to deliver the notification. What the service uses, I have no idea. There is. The entire application is written in Scala, yes. I was just thinking if there was some part of it was Java, but no, fully in Scala.
You mentioned you use Akka streams. Apparently, there is recently a new library released by Kafka, which is Kafka streams. So I think you can use it without having a cluster.
Yes, so we are not using Akka streams as a cluster as well. So we use it very simply. So in each one of our nodes, we spin up a stream. That's it. So we don't have Akka running as a cluster as well. Kafka streams, yes, they released Kafka streams recently. At the time, we were already using Akka streams. Because we were already using Akka streams, we decided to use reactive Kafka, which was then brought into Akka streams as well. So there is a very nice integration between reactive Kafka and Akka streams. I know that there are some teams that in Zendesk that are willing to take a look at the library from Kafka itself, to Kafka streams, to see, because apparently the API is really simple. Myself personally, I haven't looked at the API yet, so I have no idea if it's really better or the same, pretty much the same thing as a reactive Kafka or not. But yeah, it's another library that is out there available to be used if you just want to start with the Kafka libraries. Yeah.
Thanks.
Can I ask, are you running this in a cloud or in your own infrastructure?
So at the time, it's in our own infrastructure. I think there is plans to at some point. Huh? Sorry? It's both? No, even on... oh, that's true. Yeah, sorry. I was forgetting about 3 specific data centers. So in most of our infrastructure, yes, it's running in like bare metal, our own machines. Recently, we started shifting into AWS. So in 3 specific data centers, we are deploying this in the cloud. But again, like as in a very similar infrastructure to what we run in any other data center.
So, and I guess a follow-up then, which is maybe a strange question for a Kafka meetup, but have you thought of at some point switching to using a cloud-managed service instead of using Kafka, so Kinesis, for example?
Yeah, and that's why I was saying that we still run it in a very similar infrastructure to the rest of our data centers. So, for example, in AWS, we could use, I think the name is Kinesis or something like that. But at the moment, we are still running. So because we wanted to, when we started shifting to AWS, we wanted to have the ability to have the infrastructure as it is in every single one of our data centers. So that's, at the moment, that's what we have. We have no idea about what's going to be in the future. But yeah, I guess if we wanted to go like fully cloud way, we would start using some managed service by one of these cloud providers. Yeah.
To solve the problem of the distribution of the ticker counts, have you ever thought to add to the account ID the expected size of the account information, so that then you have a kind of hash algorithm that create the partition key in order to distribute evenly between partitions? Something like that?
Might be a good suggestion. I would have to look into it. I know that if you had, so if you had the partition size, the account size to the partition.
In some way, when you create an account, maybe I don't know how it works, but you'll have like number of user of account so you have an expected size. So this account is a big company, it will be great. Yeah. It will be a big one. So this information maybe. So to have a partition key, you start from the account ID, I don't know, and then it's a number, and then it's hashed to a key, then it's distributed evenly between 10 partitions. Like if you have kind of size information, so that the hashing algorithm can distribute evenly the key, the account ID with this. So when the size is plus 1,000, I don't know. Yeah. And so you have distributed evenly between the nodes, just as an idea. I don't know. Or at the moment you have no solution for this, or you're just doing...
At the moment, no. As I was saying, like at the moment we are just trying to understand if all the services that are like throwing data into Kafka, if they are actually supposed to throw all that data into Kafka. That's the part that we are still analyzing, because it depends on all people or all like the other teams are interested in getting that data or not, or if they might be interested in the future. That's the risk, the decision risk that we have to make. But regarding what you were proposing, it might be a solution that we could actually think about it. Just cannot forget that. So adding like the size being a number to the key, the hash will be different, of course, than the hash of the key, but it doesn't stop you from having more than one account still ending up in the same partition. And if by any chance those accounts are the biggest ones that we have, it will still going to happen unless we have as many partitions as we have accounts, which is not sustainable. So yeah, we definitely need to put some thinking into this problem. Any other questions?
Distinction between topics and partitions. Why only topics and partitions?
Sorry?
Just the distinction between topics and partitions. Why only one topic with multiple partitions as opposed to having, say, a topic per account?
So let's see. I think so. Having one topic per account. I don't know if that would be sustainable as well, because it means that whenever you let's say you provision an account in our system, you would have to go and create a topic for that account as well in Kafka, which from the operations side of it might become a nightmare to do it. The other reason why multiple partitions is a good thing is because, so let's say that you create a topic and the topic has just one partition for that account. If you want to ensure that your system, your broker, or your cluster, or your data, let's say it's fault tolerant, you have to have multiple partitions, because that's how Kafka guarantees that your data is protected against failures. So when you assign a partition to a broker, or when one of the brokers gets a partition, you can configure the replication factor of that partition. So it means that one broker is going to be the leader. But if you decide that the replication factor is 3, other 2 brokers is going to get all that data as well. So if that broker dies, someone is going to be picked up as the leader for that partition. So that's one advantage of having multiple partitions in a topic. You could, in theory, have one topic per account and still end up with multiple partitions. But in that case, you would give up on the ordering guarantees, because it means that one account data would be spread across different partitions, and you would have multiple consumers processing from each one of those partitions, which means you could not guarantee the ordering with which the events are getting to the consumers. So there's always trade-offs in going one way or the other. So in order to choose one thing, you'd need to give up on something else. That's it.
Any other question? Okay.
Okay. Thank you.
Thank you, Sergio.